into the other Python program that I'd like to talk about is called AQME, which stands for Automated Quantum Mechanical Environments. As computational chemists, we do multiple tasks on a day-to-day basis. For example, creation of input files based off of different conformers of molecules, perform quantum chemical calculations using various different kinds of packages, could be ranging from semi-empirical methods from XTB to ORCA to Gaussian. And then we need to run the specific calculations on externally. And finally, upon having those completed calculations, you have to do analysis of those specific quantum chemical calculations. And generally, it could be done utilizing this Python package of good parts, or a very basic way to start off is just understanding and doing it with Excel. But what we want to do is we want to look into ways of automating these tasks and essentially build workflows that can be incorporated within multiple platforms, softwares, file formats, which vary across different kinds of softwares, and essentially computational methods as well. What this allows is and provides is an automated and a robust recorded protocol, which could be used for within different groups and can have results which could be reproduced very easily. So what we aim to do is build a package that could just automate these tasks, which I have shown here, and be applicable for a wide range of scientific people. Some existing workflows that exist that are there for this automation have been done by various groups, computational groups. For example, the WEAST lab had the CAT-VS, where they utilized a automated screening procedure of substrate and ligand libraries to come up with different kinds of transition metal-based structures. Similar studies are also, or a similar package, I would say, is also from the Kulig lab, which is the mode simplify, which also is utilized in generation of different kinds of inorganic complexes. With respect to workflow development, the Doyle lab has developed a cloud-based workflow, which could essentially writes to the MongoDB database, where you could perform quantum chemical calculations and keep track of them in this cloud software. There are other automated workflows with respect to transition state modeling, which have been developed by the Duarte lab and the Wheeler group, where they generate new transition states based on existing template reactions. While these workflows exist in literature, what we'd like to essentially do is build a package which could be potentially used within these workflows or independently for just to do day-to-day tasks of any computational calculations. And do that along with Dr. Rekina, who's currently at University of Zaragoza, we came up with a Python package which could essentially do multiple tasks. I know there's a lot on the slide, so I'll just go over them one by one. So essentially, the 4 different modules that are present within AQME corresponds to, C-Search, C-Min, Q-Prep, Q-Core, and Q-Test, the ones which are highlighted in blue. The external softwares that we interface with are highlighted in green, and the input-output that we essentially deal with for these softwares are highlighted in gray square boxes. Just walking you over this specific workflow that we have. If you start with, for example, SMILE structure of a molecule, it could be a 2D representation, 3D representation. It could also be a non-covalent complex or a transition state itself. You could perform C-search using different methods incorporating, for example, RDKit or CREST to generate a bunch of conformer ensembles, for which if you want to do geometry refining, you can utilize the C-Min module to perform geometry refining using semi-empirical methods such as XTB or machine learning potentials such as ANI. And these conformer ensembles essentially gets saved as SDF files, which could then be interfaced with the Q-Prep module, which essentially takes in these SDF files and converts them into input files for packages such as ORCA, Gaussian, and PySCF, where you could run these input files to get your different quantum mechanical ensembles based off of different conformers of molecules, and you have your calculations run for a bunch of conformers too. And then utilizing these quantum mechanical ensembles to get out of computational energy, computational methods, packages, you could perform analysis on these using QCar, which essentially is built off of CClib, but the additional implementation in this specific module is that if your calculation fails, it will automatically give you a new input file to be which could be run again, and this loop can be done multiple times until you converge at a successful output file, for example. So this finally, as an output, you end up with potential output files from any kind of quantum packages such as Gaussian or ORCA. There's another standalone module, which is called the QTest module, which essentially is utilized in gaining molecular descriptors and properties, for example, with RDKit as, XTB as the computational chemistry package that's used. In general, this specific different modules that are present within AQME can be completely used in Jupyter Notebook, could also be utilized in HPCs to command lines. We do have ready-to-use examples and hands-on tutorials on YouTube, which you could watch and utilize to actually build workflows utilizing AQME. And then it's just a pip install away, a quick installation, which can be done. Just getting into each module in detail, I just wanted to talk through, for example, within the C-search module, you could do RDKit-based conformational searching. And with RDKit itself, you could do a regular EKTG raw method, or you could also incorporate additional methods such as full Monte, which is based off of a Monte Carlo method by rotation of different kinds of random dihedrals to get a conformal ensemble, or the sum method, which essentially rotates all possible dihedrals in the molecule to get the conformal ensemble based off of the rotations of different dihydrals. The other methods that are incorporated within C-search corresponds to methods that can be obtained from QuEST. We also have the applicability of utilizing Trajan to prune out different kinds of prune out conformers based off of different thresholds based on RMS or energy thresholds. Upon doing C-search, you could also incorporate, like I mentioned, you could do geometry refining using Cmin, which has two different kinds of methodology that can be used, which is the XTB and the ANE. With the next module, which is the QPrep module, like I mentioned, you could utilize different kinds of computational chemistry packages. But what stands out or what's new here is when you're dealing with transition metal state complexes or any kind of molecule which you need a separation in bases, for example, you generally tend to have, with respect to Gaussian, you have the definition of the different kinds of basis sets for different kinds of atoms at the bottom. This can be done in an automated procedure where you just specify that you have a specific atom for which you want to have a different basis set. This automatically gets written for a bunch of different files. For example, it could be tens of files or hundreds of files, which is automatically done. So this option of actually not manually having to add in these specific basis sets based off of atom types provides it's very helpful when dealing with a lot of files and you just want to add things at the end. With respect to processing of files, generally there are different kinds of errors that can be fixed. The errors which are fixable, essentially what that means is you get out new input files which can be utilized and run again based off of new files that are created, which for the errored files is the specific files corresponds to, the specific errors corresponds to if the calculation is unfinished, there was an SCF convergence error, optimization conversion error. If you got like a linear molecule, you got the wrong frequencies, if there's an extra imaginary frequency in your molecule, or generally if the optimization converged, but the frequency did not converge, then for these specific errors, you get out new input file, which could be run automatically in the workflow. Some errors which we don't fix are specifically mentioned on the left here. And then finally, I'd like to touch upon the last module, which is the QDEST module. So for a bunch of different conformation ensembles, utilizing the QDEST modules with like the XTB library, you can actually get out different kinds of properties corresponding to molecular properties such as homo-lumo. You could also get out atomic properties such as charges and bond properties such as bond orders, which are stored to JSON files. And also we get out results based off of Boltzmann average for these specific properties for the different conformer ensembles that are present. While I've given some background about the modules that are present within AQME, I wanted to talk through some examples that you could utilize AQME for. So for example, you have a SMILE string for a natural product here, which is like a stretching molecule, and you want to look at the output, which is the Boltzmann averaged NMR spectra, and also you want to know the conformal distribution for the specific molecule. Utilizing just 5 lines or 6 lines of code, you could move from just a SMILE string representation to the output of the NMR spectra. And the different modules that are involved here corresponds to C-search, which can be done with, which will be helpful in doing confirmation search with RDKit. You could utilize the QPrep module to generate input files, which are based off of Gaussian here. And then you could do error fixing utilizing the QCOR module, and finally use the QDES module to actually also calculate NMR calculations, and then finally get the conformer ratio. While I've highlighted one specific SMILES or one specific molecule here, this could be done for a database of hundreds of molecules where you could gain NMR spectra for different kinds of conformers in an automated manner. And another example, which I'll also highlight here, is gaining quantum mechanical descriptors for machine learning. So for example, if you have a modeling problem to solve, which corresponds to, for example, solubility of a molecule, where you have the inputs, where you have an input of CSV with the SMILES representation of the molecule and the respective solubility of the molecule, and you want to actually incorporate quantum mechanical features for modeling properties. Then what you could do is you could just, starting from SMILES, you could just C-search to get conformational ensembles utilizing RDKit and gain molecular descriptors using XTB, and additionally also Boltzmann average descriptors using the QDES module, which then finally can be incorporated into a machine learning model, for example, where properties such as homolumo could be utilized as global descriptors, atomic descriptors such as the charges could be incorporated into models to predict solubility. What this allows us to do is essentially curate, utilizing this package, we can curate a large database of different properties, which could be utilized in different kind of machine learning tasks. I'd also like to finally go through an example of just a Jupyter notebook, for example, how you could utilize AQME. The first step is essentially incorporating the different modules of AQME itself. Here, I'm going to be working with C-search, QPrep, QCOR, and QDES. For example, then the next step is, for example, with respect to the stretching molecule that I had in the beginning, just with one line of code, like with respect to the C-search class, you could get out the different kinds of SDFs for based off of RDKit, different conformers for the specific molecule. Next, utilizing the QPrep module, you could then you define the the kind of QM input that you want. For example, here we were looking at doing B3 optimization with the specific basis set. We could specify the number of processors and the memory that you want to use for the calculation. And when that's inputted into QPrep, you get the respective input files. Specifically here, we utilized Gaussian as the computational chemistry package. Next, this step is running the specific calculation has to be done externally. Generally, it's moved on to some high performance computing cluster where you run your calculations for either Gaussian or ORCA. And then finally, utilizing the QCOR module, if you just specify the path to all the specific log files, you automatically analyze different log files that are present there, and you have a list of successfully completed log files moved to a specific success folder, and the ones which have failed have been moved to a failed folder, and you have new input files that can run for the failed calculations as well. With that, and my last slide here is just a summary of what I just spoke about. Generally, multidimensional parameters, which are helpful in quantifying molecular shape, are very useful in quantitative structure selectivity relationships, and this has been shown by various examples. And to actually build these specific structure quantitative relationships, we need tools such as dubstep to actually gain insights on molecular shape. Dubstep essentially also provides a novel vector-based representation of sterics, which we could utilize to understand radially and linearly the proximity of steric effects on a specific reaction rates, for example. The other practice that I highlighted in today's talk was AQME, which is a general workflow for automation tool for different kinds of computational investigations. And the specific examples here I had was the application for the NMR studies and then building molecular property databases. And finally, both of these tools can be utilized within Jupyter notebooks and command line, as well as can be implemented along with in high-performance computing clusters as well. And what this generally allows is for a fair chemistry where you could have tools which are findable by people, they can access things, and they could reproduce results which have been specifically done for one project. You want to check or utilize the same thing for another project. These tools can be utilized across various different kinds of projects within CCAS itself, or can also be utilized by other people in the scientific community. That was the talk. Thank you.
Well, thank you, Shree. The presentation is open for discussion.
I was just going to say, I know I'm not asking a question, but there's been some interesting direct messaging and sort of updates to Annie, which I think we'll definitely look to include in the future. So thanks for those messages.
Any other comments, questions?
Shree, thanks. Thanks for the great talk, and you know, like I am very biased here because I think this work is amazing. I think I missed it, or maybe I didn't understand it correctly. Would you mind explaining Vol2Vec and Stereo-Vol2Vec again? Just that I really would like to understand it better.
Okay, monitor the website. Yeah, so Vol2Vec and Stereo-Vol2Vec is just the vectorized forms of, for example, the percentage percent buried volume and stereomole itself. So percent buried volume quantifies how much percent of a molecule is present within a whole sphere, for example. So if you have a sphere of radius 3.5 angstroms, just what percent of the molecule is present within the sphere itself. Whereas what Vol2Vec does is it breaks that sphere into concentric shells. So you have what's present in a sphere of angstrom, let's say 0.5, then what's present between 0.5 to 1, what's present between 1 to 1.5, what's present between 1.5 to 2, and you could go up on like in intervals of 0.5 up until 3. So what this allows you to do is you look at what's around, for example, the metal center, and what's further away from the metal center, and how these can influence reactivity, for example. So that's with respect to Vol2Vec. Stereo-Vol2Vec is again built off of stereomole itself, but what's constant here is the L parameter, which is along the direction of a specific bond that you're looking at, which is the blue line, the blue arrow on top. But what's new or what's different here is the B1 and B5, which are basically the perpendicular, directions to the blue vector, for example. Here, you could get what stereomole would give you is just at that. I'm not sure if you can see the part. At that specific atom, what's the perpendicular direction of the molecule? Whereas what the vectorized features will give you is again at an interval of, for example, 0.5 along the blue line. You could get out what's the length of the molecule, which would be the B1 at a specific distance, B5 at a specific distance, for example, which allows you to understand how the shape of the molecule is actually varies along the perpendicular directions of the L vector.
Thank you so much.